My talk is called Go as Practices. As you've already heard, I'm a developer from Brankas. I used to, in a previous life, be a Clojure developer. I used to do a lot of full stack work, and I used to work with a really weird database called Atomic. And then around a year and a half ago, I switched to Go and Kubernetes, and yeah, I haven't looked back. These days, I do more infrastructure and some backend work. Yeah, so why is this not a talk about best practices? Well, for that, I really like this quote by Dave Snowden. And basically, in terms of evolutionary biology, there's a lot of good evidence that suggests that avoidance of failure is a much better evolutionary strategy than the imitation of success. And this is exactly why, parables and things often have like negative consequences, or bedtime stories for kids are often a little bit dark. And the reason is because you learn best through failure. And we all attest to that, because as a kid you probably hurt yourself, like you burnt yourself or whatever. And no matter how much somebody explains to you that fire is hot, it's only really when you go near fire and you experience the heat that you really understand. So that's why I think it's incredibly valuable to learn from failure. And then the second reason why best practices, following best practices doesn't always work so well, is because what is best practice? Right? It depends on the context, it depends on the time, it depends on the stage of a company's growth. And you often see like people calling things anti-patterns in the community, like don't use the database as a queue, for example. But there's a lot of companies that very successfully use databases as a queue and don't use something like Kafka or RabbitMQ. And there's other companies that, the use cases kind of demand that they use a proper queue. But it doesn't make either of them less wrong. And I think when you think of systems in terms of, Dave Snowden likes to classify them in terms of ordered systems, complicated systems, and complex systems. In particular, software development tends to be around the complicated and complex space. And you really only have best practice in extremely rigid ordered systems. And in the more complicated and complex systems, you generally have good practice. You don't have best practice. So that's why I think it makes more sense to focus on what not to do and kind of just be able to choose practices that make sense to you rather than blindly adopting somebody else's best practice. So this is just going to be basically a opinionated list of what I think are bad practices in Go. And this is definitely something that should be challenged. What I'm really just trying to start here is I'm trying to start a conversation. This is the first iteration of this talk, and I probably haven't prepared as much as I'd like. I'll probably expand this talk in future. But the point is that these are like my thoughts on this, and I might be wrong. And I welcome anybody challenging me and just to start a debate about this kind of thing. And the idea is just to come up with a list of things that I guess most of us can agree that probably should be avoided. So the first one is large interfaces. And I think Rob Pike says it best when he says the bigger the interface, the weaker the abstraction. And I'd like to invite you to do a thought experiment. So instead of the really nice IO reader, seeker, closer, writer interface, let's just combine it all into one giant IO interface. This is obviously a terrible idea, but why is it a terrible idea? So if you look at the function do something, the first do something takes io.io, and the second one takes a reader closer. So, which do you prefer? Clearly, the first one doesn't tell you much. You look at do something, and you see io.io. It could do anything. It could read from a file. It could write a file. It might seek. Who knows what it does? But when you look at the second one, it's pretty clear that you're going to read from a file, and you're probably going to hopefully close the file afterwards. So I think in terms of understandability and readability and maintainability, it just makes a lot of sense to have smaller interfaces that can compose well together. And I think the IO interfaces in Go are particularly really good at this. So this comes from a book called The Philosophy of Software Design. It's a really great book, and he talks about modules, not Go modules, but he talks about a module as kind of like an interface plus its implementation. So what he recommends is that you have, so in this diagram, the interfaces are represented by, I should make this full screen. Interfaces are the dark gray, and functionality is a light gray, and the area of each square represents basically the amount of functionality. So both these rectangles have equal amounts of functionality, but you can see the deep module has a narrow interface and offers lots of functionality, which means the interface itself hides a lot of complexity. And conversely, the shallow one has like the same amount of functionality, but it's got a much wider interface, which makes it a lot less useful to use compared to the first one. So I like to think of deep interfaces as exactly IO, reader, writer, those sort of interfaces. And sort of shallow interfaces are the epitome of having like something like io.io instead, even though that's possibly not even the most terrible interface you can come up with. I mean, certainly some like really large interface that would be really bad, but that's just an example. So in the book, they say that the best modules are deep and accessed through a simple interface. And the problem with a shallow module is that it has a relatively complex interface, but relative to the size of the interface, there's not actually that much functionality. And the main point is that it doesn't actually hide that much complexity. And that's really what you want from an interface. Otherwise, like, why even have an interface? I mean, if you think of like your like a socket, a power socket in your house, it allows so many different appliances to connect to it, and they don't care about how the electricity on the back end is generated. Like, it could be wind, it could be solar, it could be coal, it doesn't care. And that's just because it implements like a very narrow, well-defined interface. And as such, it hides like an extreme amount of complexity from you. And I think that's what you want to go for when you design your interfaces. So the second thing that I see a lot is interface pollution. And I guess the easiest way to define this is just using an interface when you really shouldn't use an interface. So Dijkstra said that the purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. And I think this is like a really good way to think about abstraction, because abstraction isn't about making things general and vague. It's about actually reaching a level where you can be very, very precise. If you go back to IO reader, for example, you have reader, you have read, write, seek, and these are like very, very precise things. And if you look at the actual, if you looked at like a file implementation, or particularly if you go down to the Unix level, I mean, that's like hundreds and thousands of lines, and it's all abstracted away by like a simple read, write, close, seek. And I think that's pretty amazing. And that's an example of how, having a good interface gives you that kind of precision. So here's another example of interface pollution. So you see this, I see this quite often where people will they want to have like a user database. So they'll immediately start with the interface, and they'll, create this bloated interface. And then worst of all, like in the new method, they'll return like the UserDB interface. So now you've done a bunch of things. Firstly, you started with an interface. So you don't have enough examples at this point. You don't have enough data to make like a good abstraction. Like people that came up with IO Reader and the Unix like file IO interface, it didn't just happen overnight. Somebody didn't just go home and think about it, without any experience and just write that interface. I mean, it came from years and years of seeing lots of different IO, seeing like lots of complex programs use these things. And then from that, it was distilled into this interface. So there's this kind of wrong conception that people just go into like a cave somewhere and then come up with a good interface. Like, it's actually a lot of work, and I think it's really hard to come up with a really good abstraction. And then secondly, you're forcing your interface onto the implement, onto the person using your package. And Go is special in the fact that it doesn't explicitly force you to declare an interface. You can implicitly require any interface that you want. So that gives you a lot of power, because what it means is you, as the designer of the package, you can basically defer the hard work of coming up with a good abstraction that might be completely wrong for your users. And instead, you can give them the power to kind of implement whatever interface makes sense for their application. And then the final sin of this thing is that it's just not decoupling anything. It's not like the interface is exactly the same pretty much as the concrete type. So it's, again, if you go back to that deep model picture in your head, it's again like the shallow module. It's not really doing much for you. Yeah, so this is basically what I said earlier. It's just that you should really take advantage of Go's implicit interfaces. Like, they're really a really great thing. And like, I think this makes Go like really unique among languages, because I haven't really seen this before. And I think it's really important because it lets you, like I said, defer those really hard design decisions. So here's what you should do instead. You should just define the concrete type, UserDB as a struct, and return like the struct to the user, and just implement the methods, because really you don't need to have an interface here. There's no reason. So I hear some of you probably thinking like, okay, I need to mock, right? But I'll get to that in the next section. So when do you actually need an interface? Well, there's a couple of, and I took this from Bill Kennedy's post on interface pollution, which I highly recommend people read. But basically, do you need multiple implementations? So for example, I use a DB. We're probably not, unless we have some very special app, we're probably not going to be using Postgres and MySQL and SQLite, right? We're probably just going to be using Postgres. I mean, that's what 90% of apps probably do. So in this case, we definitely don't need multiple implementations. Secondly, you might want to decouple from some kind of expected change. Like maybe, your boss wants to change from using Postgres to MySQL for whatever reasons, or from SQL Server to Postgres because it's open source. If you're kind of expecting those sort of changes and your company is quite volatile, then maybe it might be a good idea to create an interface, but otherwise you probably don't need one. And then the last thing is, if you obviously have some kind of user-defined behavior which you need the user to implement, then obviously you have to have some kind of interface. So it's not that interfaces are bad, it's just that I think they're like salt. You want to use them sparingly and when you really need it. And if you want a good example, there's Arden Labs actually has a repo called Service, which I think they use for their teaching. And it's basically like a sample app. And if you like grep through that code base and you search for interface, there's basically nothing. Like the entire application doesn't define a single interface. And I think that for me is like an example of I think a well-designed app. I mean, it's a toy app, sure, but I think a lot of applications probably could do with a lot less interfaces. So back to the mocking point, I think that excessive mocking is a really bad thing. I know a lot of people love testing and love mocking. And I don't think mocking is never something that you want to do. But I think that this kind of tweet kind of emphasizes what I'm thinking, and that's basically mocks never break, and you never have to deal with a network. And I know that's partly the point of mocks, but the fact is, if you're never actually testing the real thing, then how do you know it actually works? And you kind of have the law of distributed computing where you can never assume the network's reliable, and you have all these things that you're just never testing, and your mock's never going to break on you. And basically, you don't really have 100% coverage then. Not that, it's also debatable whether you care that much about getting 100% coverage, but yeah. So you don't really need mocks. What I recommend always is just test against the real thing. Like if you're going to be using that UserDB interface, use the concrete type and test against Postgres or whatever database that you're actually using. You don't need to mock it, because then the code that you're writing actually works against the real thing. And also it lets you take advantage of the features of Postgres that you might not otherwise be able to take advantage of. I remember at an old company I used to work for, we used to test, we used to do that standard practice where you test against something like SQLite or H2 if you're in the Java world. And then your real implementation runs against Postgres. And presumably then you kind of just use a very limited subset of SQL, because obviously H2 and SQLite don't support everything Postgres does. But then we had an event store system, and we basically reached a point where we wanted we were storing kind of JSON strings in the database, and we kind of wanted to use Postgres' JSON B type, which is obviously much more performant and lets you do things like indexing. And now we couldn't do that because we're testing against H2. So eventually we did do that, but then all the tests broke, and we kind of had to make sure certain tests ran against H2 and certain tests would just not be run actually. And that was really bad. And in the end, we had to just set things up so that Postgres could spin up in a container and we could just test against it. But that's what we should have done from the start, and we would have avoided a lot of this kind of headache. And also then it really, really works in production, which I think is, it gives you a kind of confidence that you can't get, I think, from mocks. And you certainly don't want to be the guy that's debugging the really hard thing late at night. So if you do need an interface, then definitely the implementer of your package, the user of your package, can just define whatever interface they need. And this blog post is really good, gives a really nice example of how easy it is to just have the implementer define whatever interface that makes sense to them, and then test against that if they need to mock. So this is probably a controversial one. Dry, do not repeat yourself. It's kind of drilled into our heads from, it was drilled into my head at university and ever since. And people kind of are obsessive about this, not repeating yourself, extracting functions, extracting helpers. And I just think that there's nobody thinks about the overuse of this and the trade-offs that it has, because everything in engineering has trade-offs, right? There's no rule that applies to everything. So this is kind of a real example that happened in code. It's a simplified version, but I had this function upload to S3, which took a file, and it would return a path, and then the implementation itself would figure out like what the path is. I think that particular one put it at like some kind of random location in like a UUID with the file, and then we'd write that to the database so you knew where to find the file again. And then we had like 1 or 2 handlers using this. So somebody took it and they extracted it into a helper, which seemed kind of useful because it's a bunch of code, and now we have it like condensed into one place. But I ran into this really cool tweet thread by this guy Sebastian, and he's I think principal developer at Unity, and he said the number one problem in big code bases. I apologize for all the words, but it's really worth reading this. The number one problem in big code bases is entangled code dependencies. If you make code too generic or extract code too soon, you end up with more dependencies. Code used by 2+ call sites tend to eventually bloat with complex control flow, bad performance, hard to understand and modify. So here's an example of that. So now I had to add a new handler, and this handler, unfortunately, I wanted to actually specify the path myself, like where it was going to upload, because I wanted to use something like, I wanted to put the file under a particular organization, for example, and then I wanted it to be /organization and / the file when I wanted to find it later. And now suddenly the helper, is kind of getting in my way, because now I need to add this path override, and now the information gets bloated, because now if there is a path override, then I'll just use that path, and otherwise I have to do the other random implementation. So the simple helpers like actually added a lot of complexity. And if I remember in the old code, it wasn't like this simple. It was a lot more code and a lot more things that could go wrong. So as soon as you pull out a helper, it looks like it's helping, but in reality, it's just you've added a dependency to each of these functions now that they never had before. And that can be good or bad. I think this quote pretty much sums it. There's 2 types of long functions, entangled and linear. And if you avoid dependencies, then you can often write really long functions which progress perfectly linearly. Trivial to read, modify, and understand, no jumping around the code base. So if you go back here, you'll see, like, imagine this was a really long function, I'd have to like jump around all the time, like to understand the code. It's much easier if you don't have helpers from that sense. And then he says it might seem like it's a good idea at first to split like a bunch of long functions into small functions, but you ruin the reading experience and you introduce like a bunch of dependency between these functions. And basically what you're doing is you're adding risk in the sense that now, to modify those functions means that I'm potentially breaking other functions. So just everything becomes a lot harder from that sense. So I think how much to try, basically, the rule of 3 is a good default. I think if you have 3 examples, that's probably enough. But what I've experienced is that when you're in a project that's moving really quickly and code's changing quite often, then I think you probably need more examples than that, to be honest, because I've seen a lot of like dry code in fast-moving projects that just kind of gets in the way because the helpers aren't that helpful, because you end up having to modify them anyway and potentially break a whole bunch of other things. So this is a personal pet peeve of mine, which is like when I see there's no timeouts being set. And I think I blame this largely on the fact that when, like, a lot of library use is marketing, right? So people want their libraries to be used. And then naturally, when you look at the GitHub page and you look at the README, it'll show you like the simplest, most trivial example of using their library, just to illustrate how easy it is. But almost often these libraries just don't show like the production setup. So people just copy the sort of like trivial example into production code, and they don't really think about things like timeouts. And to make this worse, a lot of databases and things have infinite timeouts, probably for good reasons. Like, I'm not going to get into that, but it's just good to know that if you're not setting a timeout, the timeout's probably like infinity. So it's going to wait forever. So this is an example of setting a timeout in Postgres, and you can set like a connect timeout, and you can set a statement timeout, which will make sure that if you have a connection in your pool, that it doesn't get stuck. And this actually happened to us. We had a sign-up server, and the sign-up server was basically using Postgres, and it would get stuck. Like, it wouldn't be able to accept any connections, any new connections, HTTP connections. And it turned out that what was happening was somebody had forgotten to close like a row, and the connection pool was just filling up, and it would eventually there were no timeouts, so it would just stay full at that point, and any new requests coming in couldn't get, would try and grab a connection and would just hang. So what timeouts buy you is not getting your services completely stuck. Like it'll give your ops team a chance to see that, okay, something's clearly going wrong. Like if they're monitoring like the number, the connection pool, or they're just monitoring the service, they'll see like the performance is degrading, but it won't just like stop completely like our server did. And it took a lot of debugging to figure this out. And it probably would have been a lot easier if we had, these sorts of timeouts in place. And then naturally, I think Cloudflare has a really good post on timeouts in general that you should read. I'll try to get a whole bunch of notes up in a GitHub repo after this, or my references and things I'll eventually put up. But basically, that's a really good article to read on timeouts. But yeah, you should definitely be setting read timeout and write timeout. This also protects you against malicious people. Like a good way to check if your timeouts are working is to do a type of DDoS called a slow LoRa's attack, where you just like open a bunch of connections and slowly send bytes through, and it'll quickly tell you if you have like timeouts in place or not, because you'll soon run out of file descriptors if you don't. And then obviously on the client side, when you're making API calls, which is a lot of our job involves, like you definitely want timeouts here, because once again, you can't assume that APIs are reliable. They go down, and you need to be able to deal with the fact that they might time out sometimes. So next worst practice, I think, is not closing things. And this is surprisingly more common than you think. Like it's quite easy sometimes not to close like a database row, particularly when you want to do something more complicated and you can't just defer the close. Not closing files, and generally if you open something, just make sure it gets closed. Like make sure it really, really gets closed, because otherwise, you kind of just leak memory, and you don't want, like I said, you don't want to be the guy that has to debug, or goal that has to debug this thing in the middle of the night. Like the server's just running out of memory, and usually these are like slow leaks, so they're not really like obvious. And yeah, those are kind of like the worst bugs to debug. So I think we're getting there with tooling. Like I think static check can do some. I think somebody added something that could, but don't take my word for it, that could check if rows weren't being closed. And I think there's other linters that can check if files are closed and things like that. But it's definitely worth running those things and making sure that things are actually getting closed. So bad naming, this is probably more a general kind of worst practice in programming in general. And the two types of naming that I think are particularly bad are vague names, so calling something data or X, or it just doesn't help the person reading it. You always have to think of the person that's reading your code or maintaining your code later, because it's probably not going to be you a lot of the time. And just make sure that you name it something reasonable. And if you naming is a cognitively demanding task, and it's probably the thing that fatigues like us as programmers most. So if you can get away with not having to name something, like if you can just abbreviate it, or so it's obvious, then you should rather do that, or you should use an anonymous function if possible, and you don't have to name it. So if you can avoid naming, that's even better. It's better than giving something a vague name. And then what's even the worst ever with bad naming is wrong names, which is basically where you might name a shipment an order when it and this particularly happens. I think it's more common in like the business domain, where you just completely name things incorrectly, and then that just confuses people, and it can actually cause like a lot of bad mistakes to happen, because people are assuming this thing's an order and it's actually a shipment. And then the next worst practice is inconsistency, and this manifests itself in lots of different ways. But in general, if you call something like a parameter to a function, you call it db, and just call it db everywhere. It just makes it easy to grep the code base. It makes it easy to like understand things. Don't call something sometimes call it database, sometimes call it DB, sometimes call it storage. I mean, this is an extreme example, but you do see cases where people just name things differently, like the same thing. My dad's an architect, the building kind, and he has this thing that I really love, where he says that you can see a building was designed by an architect, because then even if it's ugly, at least it's consistently ugly. And I think that consistently goes a long way, particularly in large code bases, and particularly when you're working in a team, because that kind of being able to rely on a particular style, I think, is important. And the same goes for using libraries. Like if you see somebody's doing some kind of form handling, and they're using a particular form library, and they're using a particular validation library, and they're using a particular, I don't know, database driver, then if you have to implement a similar form on the same project, don't go and like use your own form library that you prefer. Like just stick to the style of the project. I think that kind of consistency goes a long way. And then the last point is something that I think a lot of Go presenters leave for last is concurrency, because it's quite a hot topic. But basically, overreaching for concurrency, I think, is a big mistake. And yes, partially why. There's this really great paper on Go concurrency bugs where they analyzed a bunch of huge projects like Kubernetes, Cockroach, DB, Docker, and they just went through like the issues and found all the various bugs which mention things like deadlock, or basically bugs that deal with concurrency issues. And they found that this is one of the gems that they found. I think this was from Docker or Kubernetes. I can't remember which one, but one of those. And like the problem here is that you're getting a result, presumably quite an expensive result, and then you're trying to put it on a channel, and then the select basically will sometimes, even when the result's actually ready before the timeout, if they're both ready at the same time, the timeout, the scheduler can randomly pick one of them, and sometimes it'll pick the timeout anyway, even though the result's ready. And then what happens is you can never ever, like that channel just stays blocked and causes a leak. So the fix is just to use the buffered channel. But what I really like about this bug is it illustrates how like complex CSP can be from the perspective of not making concurrency mistakes. And Go does make concurrency easy, certainly easier than a lot of other languages. But I think the point of this paper and what the paper also shows is that CSP isn't necessarily a way of making all concurrency bugs somehow disappear. And actually, when you look at the paper and the data, they actually find more mistakes being made from CSP than from traditional like mutex, locking, unlocking kind of concurrency code. So it's worth bearing in mind that even though Go makes concurrency easy, that concurrency is always going to be, as far like right now, it's always going to be difficult. And if you don't have to make something concurrent, then don't. Like there's a tendency, especially when you initially switch to Go, I mean, I felt this too, to make everything, like use a whole bunch of channels and spin up a bunch of Go routines. But really you should be benchmarking and checking, like, is this actually adding value? Because is it actually giving me some kind of performance increase? Because otherwise you're just adding complexity for no good reason. And bugs like this are difficult to debug, and you don't have to deal with this stuff you don't have to. So yeah, that's my point. Concurrency is hard, and CSP doesn't necessarily change that. Maybe it might be in the future. It might be because people are kind of used to traditional locking, and CSP is still kind of new. But so maybe the future will show us that CSP developers actually make a lot less mistakes than traditional locking. But we'll see. And also on this point, really, like a single thread on a modern CPU can do a ton of work, like a real shit ton of work. So don't forget how much work a single thread can do, or a single Go routine. And there's this great paper, Scalability, but at what cost? Where I think cost means like basically the configuration you need to outperform a single thread. I think that's what cost stands for. But basically, they wrote a really competent single thread implementation of a lot of these, like a lot of problems that like you typically use something like Storm or Spark or something like that for. And a lot of the times they could actually beat these systems until they used like thousands of CPUs basically in order to beat the single thread implementation. So I highly recommend this paper. It's worth a read. It'll change your perspective on single threaded stuff. And I actually have some personal experience with this because I once rewrote something that was processing statistics using something like a Storm cluster. And at that time it was using, I think, 3 nodes, and you had to have 3 zookeepers, the usual drill for those sorts of complex systems. And in the end, I was able to convince my boss to rewrite it as a single node with a single thread. And it actually, performed pretty much equally, and it was way simpler to run and maintain. And it went down a lot less, actually. So when you're coding Go, just remember that, a single Go routine, and most of the time you have concurrency built in because you're probably running an HTTP service or something, and then naturally each one of those are already running in their own Go routine. So you have that form of concurrency already. I work for Brankas, and we are currently hiring, so you can reach out on our career site, and